Okay, so maybe we can begin. So welcome everybody to this week's Majorana-Raychaudhuri seminar series. It's a pleasure to have Dr. Hamada from DESY, Hamburg, and he's going to talk about gravitational wave spectrum from expanding string loops on domain walls. So let us begin, and maybe I'll send you a reminder when 5 minutes are left.
Okay, thank you very much. Thank you for the introduction. So yeah, my name is Hamada. I'm a postdoc at DESY. And first of all, I'd like to thank the organizers for giving this really nice opportunity to introduce our recent work. So yeah, this talk is based on collaboration with Wakutaka Nakano, who is the postdoc in Japan. And today I'd like to talk about gravitational wave spectrum radiated from the cosmic string loops, which are expanding on the domain walls. So first of all, let me explain briefly what the domain walls are. So domain wall is a kind of a topological defect, and it is a pretty common object in the particle physics and cosmology. So domain walls are kind of a remnant of the breaking of some discrete symmetry. For example, let's consider some scalar field phi, and let's assume that this field has something like this potential, like a wave type potential, and this potential has some Z2 symmetry corresponding to the reflection of the phi. And until some stage, this phi is on the top of the potential, so this Z2 symmetry is not broken. But at some stage, this falls down to the minimum of the potential like this. Then phi takes some non-zero wave, and this Z2 symmetry is spontaneously broken by the wave of the phi. Then domain walls can appear. So, for example, you can see some typical figure from this. So, in principle, if we consider some early universe, then so different Hubble patch can take different wave of this scalar field. For example, let's say some Hubble patch takes a plus wave for this phi, and let's say another Hubble patch takes different wave, let's say minus v, and between these two different domains, there must be some boundary between these two domains, and this boundary is called domain wall. And it is well known that this domain wall easily dominates the energy density of the universe because the energy density of the domain wall is typically proportional to the a to the minus 2. Here, a is some scale factor. And of course, the radiation energy density is proportional to the a to the minus 4, which means that the energy density of the domain wall can easily overcome that of the radiation. And it can dominate the energy density, total energy density. And of course, such a case is inconsistent with the current cosmological observations. So we know that there's no much domain walls in the current universe. So this is inconsistent. That means domain walls is a kind of dangerous object in such a cosmological sense, and it must decay by some mechanism. And actually, there are a lot of ways to destroy the domain walls. But one possible decay process of the domain walls is the so-called hole nucleation. So let's consider some domain wall like this blue, two-dimensional plane. And sometimes this domain wall can decay by some nucleation of hole on the domain wall. So in this figure, this white region means that there's no domain wall, and this red circle means some boundary between the domain wall and the non-domain wall region. So this means some hole on the domain wall. And actually, this circle, this boundary, is regarded as a cosmic string. This means that some scalar field describing the cosmic string has this winding number around this cosmic string. So in that sense, this object is a kind of hybrid of the domain wall and this cosmic string. And after the nucleation, this string loop will expand on the domain wall. And actually, it will expand faster and faster because this cosmic string will eat the domain wall, which means that the energy density of the domain wall is converted or released to the kinetic energy of this cosmic string loop. So it will expand faster and faster. And when it will become sufficiently energetic, then it can radiate some gravitational wave. And actually, this is our main target today. So we will consider, what kind of gravitational wave will be radiated from this expanding cosmic string. And you might think that this looks like a two-dimensional version of bubble nucleation in the first order phase transition. This means that, bubble nucleation means that, like, in the first order phase transition, people often consider that the force vacuum decay by the first order phase transition, and the true vacuum bubble is nucleated and it will expand in a three-dimensional space, right? And it will, collide and it will radiate gravitational wave and so on. But in this case, everything happens in two-dimensional space because we have two-dimensional domain wall and the hole is nucleated on the domain wall and it will expand only on the domain wall. This means that kind of two-dimensional analog of the bubble nucleation in the first order phase transition. And actually, this setup is pretty common in many BSM models. For example, if you consider action-like particles, then such a model contains the topological defect called action domain wall and action string. And if you consider the case of the domain wall number is unity, then we can consider a very similar object. So we can consider some action string, which is attached with the action domain wall like this. Then, the situation is very, similar to this figure. Or as a second example, you can consider like more non-abelian model, like some model with some SU2 symmetry, and this SU2 symmetry can be either of global or gauge. And let's consider this SU2 symmetry is spontaneously broken by the two triplet fields, two triplet scalars, for example. Then this is spontaneously broken into the Z2 symmetry, which is the center symmetry of the SU2. And this can be further spontaneously broken into the trivial group by some doublet field charged under this SU2 symmetry. This means that this model has some two-step symmetry breaking, and this first step gives cosmic string, and this second step gives a domain wall, and so you can consider some similar setup. But this cosmic string should be diluted by some cosmic inflation or whatever, because otherwise the cosmic string, there is some cosmic string network, it will give more like a, dominant contribution. But anyway, if cosmic string is diluted by inflation, then we have only domain wall, and this will decay by the nucleation of this cosmic string corresponding to this cosmic string. So this is, another example to realize this setup. But anyway, so I would say that this model, this setup, this hybrid object of the cosmic string and network, cosmic string and the domain wall is not so special. But it's even like common in the many models. And before going to the detail, let me explain what we did in our work. So basically, we assume that these 2 points. One is that we assume that whole nucleation on the domain wall is a kind of thermal process, which means that this nucleation rate of the string loop is proportional to something like a Boltzmann factor, like this, some bounce action or some energy divided by temperature T. And we denoted this factor as some, exponential function of the time. And here, this beta is some, beta corresponds to some time scale of the nucleation process. So this is kind of analogous to the usual bubble nucleation in the first order phase transition. And the second point is that we rely on the envelope approximation, which means that this expanding cosmic string will collide to other cosmic string, other expanding strings. But after they collide, then they will disappear completely. So this is very similar to the envelope approximation in the three-dimensional case. So when bubble collide, then there's no energy density contributing to the gravitational wave in the bubble envelope approximation. So this is the same. And then based on these 2 points, we derive the analytical expression of the gravitational wave spectrum without using the quadrupole formula, actually. So quadrupole formula is a kind of very simplified formula to calculate some gravitational wave energy density, but actually we don't use such a simplified formula. We just solve we just derive the gravitational wave spectrum exactly without using this formula. Then here's our result. So this horizontal axis is corresponding to the wave number, and this vertical axis is some gravitational wave spectrum. And we found that this is our gravitational wave spectrum, and we found that this IR behavior is proportional to the k cubic, which means that this is very similar to the conventional behavior, because this IR behavior is almost determined by some causality arguments. So this should be k to the cubic. So this is consistent. On the other hand, the UV behavior is very different, very strange compared to the usual other gravitational wave sources. Actually, this UV behavior is not suppressed, but even grows linearly with respect to k. This is very surprising. And of course, this means that we need to put some UV cutoff. Otherwise, this gravitational wave energy density will diverge. So we need to put some UV cutoff. So this will not go infinitely. But anyway, it's very surprising. So this is our result. And so here, let me make some comparisons to the previous works. The first comparison is to the paper, the so-called gravitational wave gastronomy. So actually, Anish and other people wrote a very nice paper called Gravitational Wave Gastronomy. And actually, I like this title, very nice title. And they considered a lot of scenarios about the gravitational wave radiation from a lot of types of the topological defects. But one of them, they considered a similar scenario that they consider some domain wall network, and the network will decay by the nucleation of the holes. So this is similar to ours. So this is some comparison between theirs and ours. So, for example, they considered some gravitational wave radiated from the domain wall network itself, but on the other hand, they did not consider some gravitational wave radiated from the expanding cosmic string. On the other hand, in our case, in our study, we do not consider the gravitational wave from the domain wall network itself, but we consider some gravitational wave from the expanding string loop, as I showed in this slide. In that sense, this has very nice complementarities. And the second comparison is to the usual bubble nucleation. I mean, three-dimensional bubble nucleation in the first order phase transition. And of course, there already a lot of people study in such a topic. And in such a case, we have some force vacuum surrounding the bubble, and sometimes true vacuum bubble is nucleated, and it will expand, it will collide, and radiates some gravitational wave and so on. And so comparing to this setup, our setup is very different, because our setup is essentially two-dimensional process, because everything happens on the domain wall. On the other hand, the usual setup is a three-dimensional process, because bubble is a three-dimensional object. And in that sense, dimensionality is different. And this means that when you consider some maximally symmetric object, maximally symmetric configuration, in our case, this means all-two symmetry. But in 3D case, this means all three symmetry, right? So in three-dimensional system, the maximally symmetric means all three symmetry. So this gives big difference because in relativity, all-three symmetry means there's no gravitational wave. So all-three symmetry configuration does not radiate gravitational wave, but all-two symmetry does radiate, does allow the gravitational wave. Does allow the gravitational wave. So this gives a big difference in the UV, and this is why we have a very unique behavior in the UV regime. Okay, so here I give an introduction, and for the next section I will explain the bit more detail of the calculation of our gravitational wave spectrum from the expanding cosmic string loop. And after that, I will apply the gravitational wave spectrum to some cosmological discussions. Okay, so yeah, let me give some setup of our calculation. So first of all, we parameterize the metric, like some perturbation from the flat metric like this, and by using the linearized Einstein equation, this metric can be especially written down something like this. So here, this K means a projection acting on the energy momentum tensor to take transverse traceless gauge, which means we are working on a TT gauge. That's transverse traceless gauge. And by substituting this Einstein equation into this formula of the energy density of the gravitational wave, we get this kind of master formula for the gravitational wave energy density. So this means that this energy density is given by some 2-point function of the energy momentum tensor, and taking some Fourier transformation and multiply some cosine and the integration over the two time variables, and then we get energy density of the gravitational wave. And this is a pretty nice formula. But now this 2-point function means some ensemble average of the 2-point function of energy momentum tensor, because we are considering some stochastic process. And this ensemble average is basically given by the average of the whole nucleation points on the domain wall, because now the whole nucleation is like a stochastic process, and basically in principle they can happen anywhere or everywhere on a domain wall. So that means we have to take some average of over all possible nucleation points on the domain wall. But so in order to consider such a average of the whole nucleation points, we should note that there are two cases of the nucleation of the string loop. So first case is that let's consider one single hole or one single string loop is nucleated on some point. Then it will expand and hit these 2 points of the 2 points of the 2-point function of the energy momentum tensor. Let's say this R1 and R2, for example. Or another case is that we can consider the 2 string loops which are nucleated on the separated position. Like one string loop is nucleated here, and another string loop is nucleated here, and they will expand and they will hit each of the 2 points of the 2-point functions. So this can also contribute to the gravitational wave, and so we have to be careful about that. Both of them can contribute in principle, and actually they are exclusive process. That means they are completely different cases. So we have to take some summation for both cases. This is a bit tricky part. So let me give a bit more on the ensemble average. So this is basically the ensemble. Basically what we have to do is that to calculate this ensemble average of the energy momentum tensor, like on the 2 different points. Then we can get this energy density of the gravitational wave. So let's calculate this one. So basically, this ensemble average of the energy momentum tensor consists of 3 factors. One is that the integration of integration over all possible nucleation points on the domain wall. And another one is just probability for the energy momentum tensor to be non-zero. And the third factor is just the value of the energy momentum tensor. So this is just, ensemble average. So value, probability, and this is kind of summation, then you get the ensemble average. But in order to consider the nucleation points, I mean, in order to consider what kind of nucleation points are possible on the domain wall, it is better to see this kind of figure, typical, schematic figure to show some, causal structure. So here, these two orange lines, orange points correspond to the two points of the energy momentum tensor. I mean, on these 2 points, these energy momentum tensors are evaluated on these 2 points. And this vertical axis corresponds to the time variable, and the other direction corresponds to the spatial coordinates on the domain wall. For example, when the domain wall is on the xy plane, then this two-dimensional plane is two-dimensional plane is xy plane. Let's say, so this figure is like a xy plane times some time variable, for example. And this green and blue light cones, green and blue cones mean the past light cones corresponding to these two points. And this gray point means the nucleation point of the hole on the domain wall. For example, this point means some hole or some string loop is nucleated on this point, and it will expand, and sometime it will hit this point at, let's say, time t1, for example. And now we are making some assumptions, which is this loops is expanding with the speed of light, which means that we don't have to care about the finite velocity correction. And another assumption is that the initial radius of the string loop is negligible. So that means the nucleated loop is just a point, but it will expand later to macroscopic size. But at the nucleation, the size is negligible. And based on this figure, we can see that the possible nucleation points are the following. So if you consider the single loop case, which means the one single string loop is nucleated and it will hit these 2 points, then this is possible only when the nucleation points is in the intersection of the light cones. For example, this intersection is shown by this red arch in this figure, and in this red arch, one string loop can be nucleated like this gray point, and it will expand and it will hit these 2 different points. Then this can contribute to the gravitational wave. Or if you consider the double loop case, which means that 2 separated loops are nucleated on some point, then this is possible only when they are nucleated on the surface of each light cone. For example, one string loop is nucleated on this light cone and it will hit this point, and another string loop is also nucleated on this light cone and it will hit this point. Then they can contribute to the gravitational wave. And for the second factor, which is the probability, is calculated by the three different probabilities. One is that just the nucleation rate of the string loop on the domain wall, and as I said, this is given by something like this exponential function. And another one is that because we are relying on the envelope approximation, no nucleation of string loop is inside these 2 light cones. And the third one is that the third one is a bit tricky, a bit unique in our case. So this means that everything should happen on the domain wall, right? So because, for example, these 2 evaluation points should be on the domain wall. Otherwise, there is no energy density, energy momentum tensor. So these 2 points should be on the domain wall. But now we are considering some, planar object. We are considering the domain wall as a planar object, and actually they are very, randomly distributed. So sometimes these domain walls can be on the XY plane, but sometimes this domain wall can be on the XZ plane, for example, and such a configuration is completely random. So we have to take into account such a randomness of the configuration of the domain wall. This is very unique part. But anyway, we can take such a, we can calculate such a probability that these 2 points are on the domain wall. Then we get this probability. And the third part is pretty simple. So this is just a value of the energy momentum tensor. And now we are considering that the, let's say, thin string approximation, which means that when the cosmic string loop will expand, the energy density of the domain wall is completely, converted to the kinetic energy of the expanding string loop. Then based on such a approximation, we get this formula for the energy momentum tensor. Here, the kappa is some, conversion efficiency, and rho is the energy density of the domain wall. And this RS is the radius of the expanding string loop, which depends on the time. And this LS is the width of the string. And this unit vector N is pointing from the nucleation points of the string loop to some evaluation point of the energy momentum tensor corresponding to this plot. Then we can calculate the ensemble average. And here, let me give some comment on this calculation. So from this figure, you can see that if we consider the time sufficiently large time, for example, some time larger than some critical value, let's say T12, then these two light cones do not have any intersection, right? So because if you look at this region, then these two light cones have some intersection around here. But if you look at, let's say, this region, around this region, then these two, green and blue light cones do not have any intersection. So in such a case, the integration over the nucleation points become very simple because this is factorized into two parts. One is just a time integration corresponding to this direction, and just the integration over circles, because on this region, these two light cones do not have intersection, which means that if you consider some time slice, then their cross sections are just a circle, two circles, right? Circle corresponding to here and another circle corresponding here. So this is shown by this figure, for example. So this circle corresponds to the cross section of this one, and this circle corresponds to the cross section of this one, and these 2 points correspond to these two, evaluation points. And this integration just on, you can perform this integration over this circle and this circle. And this means that in such a region, the contribution is manifestly autosymmetric, because this integration is just a integration over full circles. And in such a case, you might think that such a contribution does not exist. It does not contribute to the gravitational wave because they have some autosymmetry. But actually, that does not vanish, but is even dominant in our calculation. So this is actually a big difference compared to the usual three-dimensional setup, because in three-dimensional case, bubble is nucleated and it will expand, and sometimes the bubble can have O3 symmetry, and the O3 symmetry does not allow the gravitational wave radiation because O3 symmetry is essentially the same as a static space-time. But in our case, O2 symmetry can allow the radiation of the gravitational wave. So this is big difference, and this is the key point in our calculation. But anyway, yeah. So at some region, the integration becomes autosymmetric, and it will give some dominant contribution in our calculation. And here is the result to our gravitational wave spectrum of the energy fraction of the gravitational wave spectrum at the current universe. And this is pretty complicated formula, but anyway, so I just factorized a lot of some model dependent parameters, and all spectrum, all information of the spectrum is contained in this function, this spectrum function. And we calculated this function, and we found that this is given by this very complicated formula. And actually, this is 2 months, so you don't have to, you don't have to understand. You don't have to look at the detail. So this, I just wanted to show that this is complicated. But yeah, and this calculation was pretty tough, but actually we did it. So yeah. Anyway, so we got the very complicated expression, but this is analytic actually. And of course, this expression is not good to show the result. So here, let me show the numerical plot for this function. So I plot this a spectrum, gravitational wave spectrum function, and this horizontal axis is a wave number of the gravitational wave. And this blue line corresponds to the total contribution, and this orange and the green ones contributions from the single loop case and the double loop case. And we can see that this double loop case gives a dominant contribution. And as I said, in the IR regime, this behavior is very similar to conventional case because it's k to the k cubic. On the other hand, in the UV, this is very unique. So this behaves as a k linearly. So this is not suppressed, but even grows. And of course, we need to put some UV cutoff, otherwise the residency will diverge. So, so we have to take some UV cutoff corresponding to the width of the domain wall. And beyond this UV cutoff, our calculation is not reliable. And intuitively, this UV regime corresponds to the small string loops because the UV corresponds to the microscope, very small length scale, which means that the expanding string loop is still very small. And such a small cosmic strings do not yet collide to other string, right? So because everything, string loop is very small, and the small string means that this does not yet collide to the other loops. And but this region is not suppressed because the non-collided cosmic string has some autosymmetry, right? So expanding cosmic string is a kind of completely circular object, and it has an autosymmetry. But you might think that this does not radiate anything, but actually this does radiate the gravitational wave because autosymmetry allows the radiation of the gravitational wave. And this gives some, non-suppressed contribution in the UV regime. So this is, that's why we have, that's why the UV regime, UV behavior is not suppressed, but it's growing. Okay, so far I explained the calculation of our gravitational wave spectrum. And in the next section, I will apply this result to some cosmological discussions. So this is, again, this is a result that we derived in our work. And the gravitational wave energy density or its fraction is given by this formula. So here you can see that this depends on a lot of parameters that depend on the cosmological scenarios. For example, this for example, this alpha is corresponding to the ratio of the release energy density to the total energy density, and this beta inverse corresponds to the time scale of the nucleation, and this kappa is efficiency, and this k star is the emitted wave number of the gravitational wave. And actually, these two parameters are the same as the very similar to the usual conventional bubble nucleation case. But these two parameters are very unique in our case. So this D means the width of the domain wall, and this n walls means the number of the domain wall per Hubble patch. And you can see that this highly depends on the cosmological evolution of the domain walls until they decay. So we have to specify the cosmological scenarios for the domain walls. Otherwise, we cannot predict anything. So, and actually there are two main scenarios for the domain walls. One is that the domain wall is in the scaling network, like a scaling network for the cosmic string. So in this case, everything has Hubble scale, which means that the typical length scale of the network of the domain wall is Hubble scale. And this scenario is not insensitive to the initial condition of the domain wall because it doesn't depend on how the domain walls are produced in the past, because so you don't have to care about the how produced the domain walls. So after the production, the domain walls will approach the scaling network, scaling regime. Then everything is like just given by this Hubble scale network. On the other hand, there is also another case that the domain wall is not in the scaling regime. That means the domain wall can form some network, but such a network is not yet in the scaling regime. So in that case, yeah, as I said, the domain walls are not yet approaching the scaling. And in such a case, the configuration highly depends on the production of domain walls, because the configuration still contains some of the information about how produced the domain walls are. And for these two cases, actually this case has less domain walls because everything is Hubble scale, and basically the number density of the domain wall is pretty dilute. So in that sense, that we have less domain walls and they radiate less gravitational wave. On the other hand, in this non-scaling case, in principle, we can have a lot of domain wall, and in principle, they can be dense, and they can radiate the more and more gravitational wave compared to this case. So let me consider the two independent scenarios. So first, let me consider the scaling network of the domain walls. And as I said, in the conventional scaling of the domain wall network, the number density of the domain wall is basically order 1 for Hubble patch. This means that this parameter is set to the order 1, and the energy fraction is given by this expression. And using these parameters, we can calculate the gravitational wave energy density radiated from this expanding string loop. Then we get this expression. And here we took some UV cutoff for the wave number. And actually, there are also another contribution. There's also another contribution of the gravitational wave from domain wall network itself. So this figure this figure shows some domain wall network, and as I said, as I stated in the introduction, so Anish and his collaborators calculate some gravitational wave from the domain wall network itself. Then such a energy density is given by this expression at most. And comparing these two expressions, we can see that our gravitational wave radiated from the string loop is insignificant because we have some suppression factor here, and this is actually pretty small because this basically the ratio of the domain wall width and divided by the Hubble radius. This is pretty small. So in that sense, our gravitational wave is insignificant for the scaling domain wall network compared to the gravitational wave from the domain wall network itself. Then let's consider another case, the second case, in which the domain walls are not in the scaling regime. And so in this case, let's make some two big assumptions. One is that the domain wall is produced in the non-thermal way, which means that the domain wall is not produced in the thermal fluctuation or thermal phase transition. Instead, the domain wall is produced by the non-thermal and in a non-thermal way. And for example, this figure corresponds to the shows some scalar field describing the domain wall, and at some this is not in a thermal bath. And until some stage, the Hubble parameter is very large. That means this scalar field cannot roll down to the minimum of the potential due to the Hubble friction. But when the Hubble friction becomes small and becomes comparable to the mass negative curvature of the potential, then these fields can roll down to the minimum. Then the domain walls are produced by this mechanism. And in this case, the width of the domain wall can be comparable to the Hubble radius at that production stage. And another assumption is that, as I said, the domain walls are not in the scaling regime. So domain walls are produced, but they are not yet in the scaling regime. And in such a case, the domain walls can be very dense. And at most, this can have very, very large number per Hubble radius.
Sorry, we have 5 minutes left.
Okay, thank you very much. Then, based on these two assumptions, we can have a very enhanced gravitational wave like this. And let me see. And so this is the prediction of the gravitational wave spectrum in our calculation. So as I said, I assumed that the domain walls is not in a scaling regime, and the domain walls are produced in a non-thermal way. Then we can have the enhanced gravitational wave, and this plots correspond to some 3 benchmark cases. And here we take some, the temperature of the universe at the whole nucleation is around the 10 MeV, and this beta is taken as this value, and maybe this is the most important. So this D corresponds to the width of the domain wall, and we took some, 3 benchmark cases for this, corresponding to these 3 lines. And also we should put some UV cutoff, otherwise the energy density will diverge. So we took UV cutoff like this 1/, width of the domain wall, and beyond which our calculation is not reliable. And you can see that this blue line can nicely fit the reported PTA signal. So this means that this case can explain this case can explain the PTA signal. And also for other cases, this is in a range of the expected range of the future gravitational wave observatories. So we can expect that this kind of very strange, I would say this strange spectrum can be detected by the future gravitational wave observatories. Okay, this is our result. So so as I explained, we consider the expanding string loop on the domain wall like this, and this expanding loop can radiate the gravitational wave, and its spectrum is pretty strange, very unique. Like this has a K2 cubic behavior in the IR, but this has a K linear behavior in the UV. So this is very unique. And the key point is that unlike the 3-dimensional case, in our case, everything happens on the 2 dimensions. That means sometimes this configuration has autosymmetry, but autosymmetry does allow the radiation of the gravitational wave. So that's why that's the reason of this big difference in the UV regime. And this is the prediction of our scenario. So and I showed that by taking some appropriate parameters, this spectrum can explain the PTA signal. Yeah, that's it. Thank you very much.
Okay, thank you for the nice talk. And we have time for a little bit time for question answer. Anybody in the audience want to ask? Please unmute yourself and ask.